Barbara, an expert on magnetohydrodynamics, radiative magnetohydrodynamics, and please welcome Omer.
Thank you. I just heard speakers though. Do I have an hour or?
You have half an hour.
I have half an hour.
Nobody told you that.
Nobody told me that. Okay.
Every other talk.
I'm really sorry you have to read the email till the very end.
Okay.
We will not ask this.
Okay. So I prepared an hour-long talk, but I will work it through. Forgive me for changing the title of my talk. I originally wanted to talk about dwarf novae as well, which are accretion disks around white dwarfs, because that's, I think, where I am most excited about the opportunities of comparing observations with theory. But this is the Black Hole Initiative, and at the last minute I decided, I should really talk about what I'm doing on black holes, which this is... The black holes I'm talking about are supermassive black holes, so I'm talking about active galactic nuclei, although I am not talking about Sag star or anything like Sag star, which is a very underluminous source. I'm going to very, very high luminosities, so where radiation is incredibly important. Let me mention my collaborators in this work. Shane Davis is a former graduate student of mine at the University of Virginia. Yanfei Zhang spent some time here at Harvard.
This is a picture from here.
Indeed. So yes, he's an import to us from Harvard. Jim Stone and a student of mine, Zhang Zhang. Okay, so if you know anything about accretion flows onto black holes, you may know that they are thought to come in three types. The standard type that most people think about are geometrically thin, optically thick accretion disks, so they emit mostly a thermal spectrum. When you go to higher luminosities, they start to inflate and become radiation pressure supported, and it is thought that photons get trapped in the accretion flow and impacted inward into the black hole. And then Ramesh is responsible for these low luminosity systems, which is probably where Sag star lies. So it's again a geometrically thick flow, but a radiatively inefficient flow. So it's again a very hot gas where a lot of the heat is thought to get infected into the black hole. I am again working in this region of the, and that's what this talk is going to be. Well, in this region, so at high luminosities, and I'm going to show you that much of what we know in this regime, especially for active galactic nuclei, for supermassive black holes, is in fact wrong, in my view. And that might explain the problem that we've been facing in dealing with AGN for a long time, and that our theoretical models do a really lousy job of explaining the observations. I'm sure the models for Sag star will be great, though. When the EHT, yes, I'm looking at you.
I'm not talking about Sag star.
I am not talking about Sag star.
They are also.
It's all going to be on M87? The rumors are flying.
No one knows. It could be about something entirely different.
Moving on.
Omer, EHT is going to be observing white dwarfs. You should have talked about dwarf noise.
Okay, so sorry, that previous slide was just to emphasize that we don't really understand how AGN work. So supermassive black hole accretion at high luminosities. I want to go through this argument to explain what I view to be the big problem here that makes AGN different from other accreting sources. And so I'm not even going to use standard accretion disk equations. I'm going to assume that they're radiating at about an adding to luminosity. We observe that actually in many quasars. If they're emitting at a luminosity where radiation pressure is comparable to gravity, it means that they're probably in a very, very geometrically thick flow. That's all I'm saying. I'm going to assume that the infall velocity is alpha times the free-fall velocity. That's an ansatz that Martin Rees invented in 1984, so that's where my alpha parameter is coming in. It's just a ratio of infall speed to free-fall speed. I'm going to work near the black hole. I'm going to assume mass conservation. I'm going to assume for the moment that gravitational binding energy that's released is put into luminosity with an efficiency of order unity, and I'm going to assume that photons diffuse outward. Just with those assumptions, I'm not making any assumptions about angular momentum or the geometry. I can work out what the density and temperature in the flow is and how they scale with mass. Yes?
So are those sort of universally accepted assumptions in astrophysics?
That
The ones on the last, is that,
in astrophysics, so
or in astronomy, or?
okay, so this is observed, Andy. So the luminosity we see Eddington luminosity sources in active galactic nuclei.
Right.
That by definition means the radiation pressure is comparable to gravity. This is the only thing, this is merely a parameterization of how rapidly the infall is occurring, and I'll see how that parameter affects things.
That's empirical. That depends. That varies across systems.
It is the physics behind that is okay. In dwarf novae, we know something about this. In other systems, we don't really know a lot about what that parameter is. In dwarf novae, we do, and that's and we think we now, or I think we now, understand the physics that's responsible for that, and for how it varies in different sources. So yes, I would claim that we do know something about this. In active galactic nuclei, we know very, very little, okay, which is why I'm trying to make general assumptions. So is mass conservation widely assumed in astrophysics? Yes. Is this I'm assuming that it's radiatively efficient. If it isn't radiatively efficient, I have to drive even more mass down.
But the fact that all the energy is from gravitational binding energy, is that generally?
Yes, that's so what would be the alternatives?
Spin.
I don't know.
Spin.
Spin is certainly something as well that you could tap into. That's right. Yeah. Okay. So anyway, with these assumptions, I'm just going to make a very simple point here. If I compare gas pressure and radiation pressure within this fluid flow, gas pressure goes as density times temperature, which goes as the black hole mass to the -5/4. Radiation pressure goes as T to the 4th, so it goes as m to the -1. So if you move to supermassive black holes compared to stellar mass black holes, radiation pressure is that much more important than gas pressure. And it can approach values of order 10 million for a supermassive black hole of 10 to the 8 solar masses. And I've only made those very, very simple assumptions to reach that conclusion. And if you use standard accretion disk theory, you basically end up with the same numbers and the same scalings, okay, except now that I have an Eddington luminosity ratio here. I think the problem with our theories of AGN accretion flows is that we don't understand high levels of radiation to gas pressure ratio and how they affect the flow. That's all I'm trying to say here.
But stars have that.
Stars
Massive stars
do have that. And stars, we also don't understand very, very well, although we're beginning to, yes. That's indeed, that's true. Okay, so I have half an hour. Okay, so let me just I'm not even going to review these things then. So the first half of my talk was to go through these problems that we're having to face that that have always been a source of uncertainty. So let me just briefly sketch this for you. Radiation pressure only depends on temperature and under optically thick conditions. It does not depend on density. A radiation pressure dominated medium, therefore, doesn't care if you create density fluctuations all over the place because pressure doesn't care. And radiation pressure dominated media spontaneously produce strong density fluctuations everywhere. We know that, we see that in zillions of simulations. They create such density inhomogeneities can allow photons to get through much more quickly, so it's maybe difficult to trap photons. And in fact, we see evidence of that in simulations. These accretion disks, which are radiation pressure dominated, are supposed to be thermally unstable according to classical accretion disk theory. And that has now been confirmed by simulations, but there may be mechanisms by which you can stabilize the flow. I'm going to talk about this later. If you have a radiation pressure dominated medium, it's likely that you're going to drive alphas. If you're anywhere near the Eddington luminosity, that means luminosity, radiation pressures can exceed gravity if you exceed the Eddington luminosity. And so we expect outflows, and in fact we observe outflows in AGN. And finally, let me just mention this. So a very simple argument for the string theorists. The gas in this room, the nitrogen molecules that make up the air in this room, their microscopic velocities are moving at a velocity that's comparable to the sound speed, and it's simply because that is their mean RMS velocity, and that is the formula for the sound speed. It just goes as temperature divided by mass. And so if I'm talking about an electron ion plasma, it's the RMS velocity of the electrons basically goes the gas sound speed times the square root of the proton to electron mass ratio, because the protons are what actually carry all the inertia in an electron ion plasma. Turbulent velocities in these accretion flows, which we think are generic, the presence of turbulence, basically go as the gas sound speed times this ratio of radiation pressure to gas pressure. And so what this means is that I can have bulk turbulent motions which can exceed the electron thermal motions if I just have a radiation pressure to gas pressure ratio that exceeds the proton to electron mass ratio of 2,000. And I just showed you that AGN have that ratio going up to 10 million. So that means that bulk motions in the gas can Comptonize the photon field and affect the spectrum that emerges. And conversely, if photons are Compton scattering off of those bulk motions, they can damp those bulk motions. And so there's a radiation viscosity that acts on these flows. And I will show you that this turns out to be important. Okay, so I'm going to skip radiation methods, just to say that I will acknowledge that there has been incredibly great work here done at Harvard by Ramesh Narayan. Forgive me, Ramesh. And what I was thinking.
The work was done by Sadowski.
Minus one letter.
These, I think, are the most sophisticated simulations of these radiation-dominated flows, including the full effects of general relativity. But they have used a treatment of the radiation that is based on basically taking moments of the radiation field and not solving the full radiation transfer. They do incorporate all the effects of general relativity, though, and these are very, very important. Because I'm going to be focusing particularly on the effects of radiation pressure, we're going to be using less general relativity, in fact, no general relativity. I'm going to mock, okay, so all of you who are really into GR or anything, you can walk out of the room right now. We're going to mock up GR with what's called a pseudo-Newtonian potential, which was introduced by Bodo and Pachynski many years ago. But we're going to solve the full radiation, the kinetic equation, the Boltzmann equation for photons in our simulation, and integrated over all energies. And this is because we really care basically about off-diagonal components of the radiation pressure tensor, because I'm particularly interested in these radiation viscosity effects. Okay, I'm going to skip that too. I'm going to skip this too. Skip the fact that the simulations done by my collaborators before I joined this collaboration get radiative efficiencies which are 10%, even well above the Eddington ratio, and I think this disagrees with observations because quasars never exceed the Eddington limit. This is the black hole mass versus luminosity, and this is the line where radiation pressure balances gravity, and all AGN are basically below this line. They have less luminosity than the Eddington luminosity. But when I joined this collaboration, we're about to submit a paper this week on sub-Eddington accretion. Okay, so let me point out what this is. This is an azimuthal slice through two simulations, time average, showing you the time average density structure here and here. We've only run two simulations because they're very expensive, because we are solving the full kinetic equation for the photons. But right away, those of you who are experts in accretion disk theory should immediately recognize this is the photosphere, that these are not standard accretion disks. Because a standard accretion disk, that is where radiation pressure is balancing gravity, should have a flat scale height profile, independent of radius. And that's simply because the local flux that's released from the release of gravitational binding energy exactly matches the local vertical gravity, and so that it gives you a scale height that's independent of radius. That's not what's going on here or here. This is the accretion rate in units of Eddington defined with 10% efficiency if you care, as a function of time, so they've reached a sort of steady state. Those are the luminosities. The luminosities, their radiative efficiencies are around 1% here. And they are thermally stable, even though radiation pressure dominated disks should be unstable. Again, I won't go into the details here because I want to focus on this. Okay, so I have 13 minutes. Oh boy. Okay, so again, I want to point out this scale height dependence, which is not constant. This shows you the radiation energy density. You'll notice that there's this interesting feature here, the radiation energy density. It seems to be higher at higher scale heights. Oops, I just went through here. Let me show you what's going on. So this is a radial profile of vertically integrated pressures of various sorts. The radiation pressure is in red and the magnetic pressure is in black. And the thing that you should notice here is that the radiation pressure is basically the same as the magnetic pressure, both here and here. And in fact, here the magnetic pressure exceeds the radiation pressure. If you look at the vertical profile at a particular radius, you can see that the radiation pressure is virtually flat and the whole disk is actually supported by magnetic pressure, not by radiation pressure. Okay, so these are magnetically dominated flows. And this is a big thing that nobody has ever really, well, I won't say nobody, but has not really been included in classical accretion disk models of AGN.
Isn't the gradient matters?
Exactly, it's the gradient that matters. The magnetic pressure gradient, and there's no gradient in the radiation pressure. Isn't that interesting? I wonder why that is. Yes, so not only is the radiation pressure, yeah, it's comparable, and it's much bigger than the gas pressure, as I proved to you earlier on, but yes, there's hardly any gradient. Why would that be? So, because it's transparent, right? Of course it's transparent. No, it's not transparent. The optical depths are bigger than unity everywhere. Another difference between this and classical accretion disks is that the optical depth in classical accretion disk theory should decrease with increasing accretion rate, but that's not true. The optical depths at higher accretion rate are actually larger, but they're both optically thick, okay? In this case, yeah, it's maybe 2, in terms of the scattering optical depth, but once you get out away from the inner regions, it's plenty optically thick. So another explanation, you've got to be able to guess this out. Well, there's turbulence, yeah, but what? But so what?
It makes the temperature constant.
No. Only if photons. The turbulence is dissipated.
So, photon viscosity.
You're warm. There was another question back here.
Yeah, 0.07, 0.2, that's alpha?
No, so 0.07 is referring to the accretion rate in units of Eddington. So the only thing you really need for these numbers is that this is a brighter disk than this one. This is accreting at a higher accretion rate than this one. Okay, you're very warm, Avi. That's the punchline. Okay, well this is getting close to the punchline, and this is the key. So this is the radial profile of accretion rate in units of Eddington, and the accretion rate is negative, so higher accretion rates are more negative. So the total accretion rate is here, it's around 0.07 in units of Eddington, which is why this is called 0.07, and it's around 0.2, which is why this is called 0.2. But you'll notice that we've split the accretion rate into where the mass flow is above the photosphere and within the photosphere. And so in optically thick regions, the accretion, in this simulation, the accretion rate is actually very small compared to the optically thin regions. So what I have here is I have a surface layer of accretion going down the disk, and all the dissipation of the release of accretion power is actually happening in optically thin-ish regions. And so why is the radiation energy density flat? Is because you're dissipating above the photosphere and radiation is diffusing in. It's like an externally illuminated protoplanetary disk, which also has an isothermal profile. And it's pretty uniform outside too because it's optically thin. It has surface accretion. And now the question is, why is that? Because radiation viscosity is dominating. So I have 10 minutes. I can slow down now. So I managed to leap through all the introductory slides, which means I've already lost all of you. But I can go through some of the punchlines now. So this is a stress measured in units of thermal pressure. Again, radial profiles, and you can see that in this particular simulation, as I shell average the stress as a function of radius, I actually have this off-diagonal components of the radiation pressure tensor are dominating the off-diagonal components of the magnetic field, the Maxwell stress tensor, and the Reynolds stress tensor, which is in the dashed line. In this simulation, it's actually magnetic stresses that dominate, but still the radiation off-diagonal components are contributing substantially, much more than the Reynolds stresses in the gas. And so why is there photon viscosity? So here's in that lower luminosity simulation, I'm actually showing you cross-sections of Maxwell stress, Reynolds stress, and the radiation stress, both components in R phi and theta phi. This one is less relevant, but this is and you can see that there's substantial radiation stresses here just above the photosphere where the surface accretion is going, and it dominates the stresses. So it's actually mediating, or as a result of, this surface accretion. I'm not sure which way the causal behavior is going.
This is similar to protoplanetary disks where you see there is a dead zone in the middle
and an active zone because of ionization in that case, and that you're right, because MRI is active up there. Yeah, in this case it's photons, and it's the, I think it's obvious. So this is, I'm going to acknowledge your work with Ari Leor in a second. I think it's because up here the photons have a larger reach to sample larger velocity shears because of their larger mean free paths, and that's what gives them an advantage. Okay, so yes, there you are. You're acknowledged. So this was a suggestion actually by Avi and Ari Leor many years ago that this would be an important process in supermassive black hole accretion, although you were thinking at the time that it would be relevant for geometrically thick flows and not so much for geometrically thin flows. But because of this fact that you can do this just above the photosphere, that's the trick, which I don't think was anyone anticipated. It actually turns out to be very, very important. And we can estimate this, and I won't go through the formulas here because of lack of time, of just, is the photon energy density enough to drive substantial off-diagonal components? And it more or less, the solid curve indicates the results from the numerical simulation, and the dashed curve indicates our estimates from radiation viscosity. Yes, it flips negative a little bit here, but at least well above the photosphere and in the optically thick regions, it matches the numerical simulations perfectly. Well, pretty perfectly. Because there's surface accretion, there's a lot of dissipation, the outer layers also get very, very hot, up to temperatures of, several times 10 to the 8 Kelvin, so we're talking tens of kilovolts. It's not a full AGN corona, which would get up to 100 kilovolts, but it's up there. And it becomes more radially extended as you lower the accretion rate, which I think is consistent with the alpha OX trend in AGN, that as you lower the accretion rate, lower the Eddington ratio, you get more X-rays compared to ultraviolet. And again, it's because of the surface accretion that's mediated by photon viscosity. We've done a Monte Carlo simulation of the resulting spectrum that comes out, although because these simulations take a long time to run, we had to cut out the regions which were basically full of soft photons that were from the initial condition. And you can see that even in the Monte Carlo simulations, we see these off-diagonal components of the stress tensor, although you can see the noise in the photon trajectories, and the overall spectrum, and you can see that there's a substantial amount of X-rays here, but again, we're only talking about tens of kilovolts, so it isn't a full AGN corona, but it's in that direction. Wow. This is the first time I've compressed a talk into half an hour in my life. So just to summarize, luminous active galactic nuclei accretion flows are dominated by radiation pressure, okay, by many orders of magnitude. And I think if you really want to understand the complexities of such flows, you have to do simulations with proper treatment of photon transport, although our neglect of general relativity is going to be is a critical flaw, and that needs to be rectified. We find, even though radiation pressure dominates the thermal pressure, that our simulations are magnetically dominated. And this has actually been seen by other people. People like Sasha Tchaikovsky, when they actually try and run thin accretion disks, they often end up with magnetically dominated flows. And this is another aspect of the
Oleg Sandowski was the first one to do it. Yeah.
Yes, and in fact, let me, to be absolutely fair to Oleg, because this is one of the slides that I was forced to skip, but I feel that I need to do this.
Not with me, he did it alone.
Yes. So when I zip through this stuff on thermal stability, strongly magnetically pressure supported disks can be stabilized. Sadowski 2016. Yes, I'm well aware that he was the one. And let me mention, I think that is why we're not seeing any evidence of thermal stability. It's not opacity effects, although they are there. It's this. And he was right. Yeah, so he anticipated this and he is correct. And in fact, frankly, let me mention this. I think this is the solution to soft states and X-ray binaries. Why there are no thermal instabilities there, this is the answer. Oleg, I think, was underappreciated. Okay, let me get back to my summary. So we get surface layer accretion, and therefore dissipation is happening right in the photosphere. That's perfect for generating a corona at lower Eddington ratio, leading to almost uniform radiation pressure inside the disk. And I think we might be able to explain the alpha-X relation. And the question is, what happens further out from these regions? And we need to start exploring that. And I will stop there. And forgive me for a very rushed talk.
You're the first speaker at the BHI to end on time, actually.
But you didn't tell me that.
Congratulations on the podcast you were giving it. We have time for at least one question because of this very well timing.
If anyone understood anything from that, that's
so, Omer, I think you were too modest, because actually the most impressive part of your work was the explanation of the X-ray emission from quasars, which is always was always looming in the background. I mean, the alpha disk was never able. So people made analogies with the sun, like you have reconnection above the disk. There was work by Jeremy Goodman and others. But you're actually providing a very natural origin for that, which has to do with photon viscosity, nothing to do with reconnection events.
Right, and it's something that makes AGN special compared to X-ray binaries.
So that is a new message that I don't think anyone else appreciated before. That's
Thank you.
Very important.
Thank you, Avi.
So, Omer, the radiation and the gas and the magnetic field are all included in the simulation.
Yes.
But what is the thermodynamics? Are they all at the same temperature? Are you assuming black body? How exactly are you handling it?
So we're assuming black body in the sense that we're only dealing with the effective temperature of the radiation, because we're doing a frequency integrated treatment of the transfer equation. So that's why I had to show you a Monte Carlo simulation to actually calculate the spectrum. The temperature, the energy, the gas and photons are allowed to have different temperatures mediated by Planck mean opacity effects. That's pretty effective, actually, in coupling the gas and radiation temperatures, so they're mostly the same until you get above the photosphere, and then the gas temperature starts to skyrocket because there the coupling is not sufficiently efficient, which is why we can get a hot corona.
So I guess I thought that was the answer. That's more or less what we also do.
Yes,
in
right.
our course,
Yes,
right?
yes.
So my question now is, you've got this radiation viscosity. So viscosity, of course, transports angular momentum. It
Yes.
also dissipates energy.
Yes.
So when you have a radiation viscosity dissipation, does it go into the radiation, or does that energy go into the gas, or where does it go?
I think it goes into the gas.
Okay.
Yes. And the question is, where in the code does that happen?
Yeah.
It's really what you're asking.
Well, also in the physics.
Yeah. Well,
Both. I would like to understand both.
Well, in the physics, there's it's the stress times rate of strain, which provides, it's a viscous heating rate. It literally is. So,
Which fluid gets it? That's what.
Yeah. Right.
So there is a rate of dissipation, but where does it go? Which
Right.
fluid is absorbing the energy?
I believe it's the gas.
Even though most of the energy density may be in the radiation.
That's right. Yes.
Okay.
Yeah.
It's the inertia, doesn't it?
Yes.
I would like to think about that.
Yeah,
Not at all
I
obvious.
don't. Right.
And the last question.
I agree that it's not at all obvious, and yes, I can. Yes, in this, it would be nice to talk to you more about that. Yes.
Very basic question.
Yes.
So, when you add in GR, then the spin of the black hole will affect the
Absolutely.
simulation.
Right.
So is that I thought that was supposed to be a big effect, or are you saying that the spin of the black hole doesn't matter?
So again, we talked about this very briefly at the beginning of the talk when people were asking me questions. So yes, the spin of the black hole can be a very powerful source of energy, and that is not being included in these simulations at all because they actually don't include general relativity. So yes, that is something that will be interesting. And the full GR-MHD simulations that have been done by Ramesh and his collaborators do see evidence of extraction of black hole spin energy into accretion. Well, not into the luminosity generated by these accretion flows. So yes, that does happen, and it can be a big effect. And we're not including that all here in what we've done.
Omer is around for the rest of the day. You may try to catch him and chat some more about the subject. Let's thank the speaker.
Please introduce him.
Is there a procedure?
Yeah, here, right here.
Oh, you need the BHI?
Here, it's right here.
Actually, it was not noticed.
But no, it's not.
Because you simply didn't see that.
Yeah.
At least there hasn't been a bug with it. And if it is, it'll be fine. Just be a little bit green. But I don't think there is with the ID level.
Okay.
That's not fun.
That's a little bit fun.
Did I have done this before? Yeah.
Maybe it's the different thing.
Oh,
Instead of HD, man. Oh, good.
right. So our second speaker is Paul Chesler. I guess everyone knows Paul. He's a Black Hole Initiative Fellow in physics, and today he will tell us about his new work on the internal structure of black hole created by a collapse.
Good. So I'm going to tell you about some work that Ramesh and Eric and I have been thinking about for the last year or so. The basic problem that I want to ask today is if I have some distribution of matter and it collapses and forms a black hole, what is the final state of the system? In particular, what is the final state of classical gravitational collapse within general relativity? So for pedagogical reasons, I'm going to focus almost entirely in this talk on spherically symmetric collapse, although essentially everything I'm going to talk about will generalize to rotating black holes, and I'll talk about that at the end a little bit. And to keep things non-trivial, I'm going to talk about spherically symmetric charged black holes, things that end up looking like Reisner-Nordstrom black holes, because those are, in essence, the poor man's version of Kerr. They have inner horizons, they have Cauchy horizons, and so on. So what is the final state of collapse? In the exterior geometry, if I have some charge distribution of matter, it's widely believed, it's accepted that the exterior geometry will relax to Reisner-Nordstrom. And there's essentially two trivial relaxation mechanisms. If you have collapse, not all the matter and energy will initially be behind the horizon. You might have some radiation outside the horizon. And that radiation can propagate to infinity, or it can be absorbed by the black hole, thereby allowing the system, the external geometry, to relax to equilibrium. The actual time scales associated with relaxation you can reason through as follows. This outgoing shell of radiation, as it propagates outwards, some parts of that will scatter off the gravitational potential of the black hole, resulting in infalling radiation that has to decrease as a function of time, simply because the gravitational potential becomes weaker at infinity. And it was reasoned long ago in the 70s that the infalling radiation near the event horizon decreases with an inverse power of time, inverse power of advanced time, v, with the power p depending upon, in essence, the spin of the field. So low spin fields like a scalar decay slowly, high spin fields like gravitational waves decay more rapidly. So that's the basic picture for the exterior geometry. What is less clear is what happens in the interior. Can the interior relax in any meaningful way to the Reisner-Nordstrom solution? So it's easy to reason the answer is both yes and no in some sense, and the cleanest way of doing this, at least that I could think of, is to draw a congruence of outgoing geodesics in the Reisner-Nordstrom space-time. So here's the Reisner-Nordstrom geometry written in infalling Bennington-Finkelstein coordinates, where lines of constant time v in this plot are radial infalling null geodesics. R here is the radial coordinate. It's an aerial coordinate. R will always be an aerial coordinate in this talk, meaning surfaces of constant R have area 4 pi r squared. The Reisner-Nordstrom geometry has two horizons. It has an outer horizon which is an event horizon. Light rays, outgoing light rays just outside the outer horizon can escape to infinity. And just inside the event horizon, the outgoing light rays always propagate to smaller values of r. Okay? So if I consider now some sort of perturbation, which is on this time slice right here, suppose it's localized in this region right here, as a function of time, that perturbation flows to the to r minus. It always flows to r minus. And so what this means is that the geometry exterior to r minus can relax to the Reisner-Nordstrom solution. There's a mechanism by which perturbations can be transported away. However, because this perturbation here is becoming exponentially localized at late times, it follows that any perturbation that flows to r minus must become exponentially blue shifted by a factor of e to the kappa v, where kappa is the surface gravity of the inner horizon. And so what this means is that if I start off with some arbitrarily small perturbation here and evolve it forward in time, there will inevitably be a late enough time where the back reaction of that perturbation is non-negligible. So in other words, this whole region right here you should regard as being unstable. Okay?
A question, there is also another radius where the electric field will break down.
You're talking about due to quantum mechanical effects?
But I guess that is ignored here because you're doing classical. But
we're doing classical.
But in reality, there would be a place where electron-positron pairs would be produced.
Right. Absolutely. There'll be a place where QED effects are important, and that'll be deep within here. Right. So the picture, the cartoon to have in your mind here is that at late times in the gravitational collapse, the geometry exterior to r minus should, up to some power law decay, relax to the Reisner-Nordstrom solution. And that at r minus, there is what you might want to think of as a classical firewall of exponentially blue shifted energy. And inside r minus, it's anybody's guess.
Why do you say at r minus? Isn't it as you approach r minus from above that the exponential growth occurs?
So you can see just quite clearly from this picture. Suppose I started off with some initial data with some perturbation right here. That perturbation becomes exponentially localized at r minus. So when if I jump into the black hole, I don't see anything special happen until I get exponentially close to r minus.
But still, at when you say approach something, so if you go to r minus from above, you're going backward in time, aren't you? From below, you're going backward in time, right?
So going forward in time is like this.
Going forward in time is like that.
Yeah, I'm talking about infalling observers right now, not outgoing observers.
So if you're going forward in time, as you approach, I thought what you just said was that as you approach, you would be approaching r minus from above.
Yes.
You would see the perturbations getting more and more singular.
Yes.
That sounds like it's not approaching Reisner-Nordstrom.
Well, what I'm saying is it happens exponentially close to r minus. Right.
It happens exponentially. But where does it approach Reisner-Nordstrom in the intermediate region?
For the intermediate range, what?
Between r minus and r plus.
So in this, if I go to arbitrarily late times, my claim is that in a region that is, except for a region which is exponentially close to r minus, with this sort of exponential right here, the geometry will be described by the Reisner-Nordstrom solution. Okay. So let me move on though, because that'll actually be, it turns out that's a fundamental assumption. It's supported by numerical simulations too. We can talk about it more at the end. Does that sound okay?
But the fact that they're diverging isn't evidence for the fact that some modes diverge near r equals r minus isn't evidence for stability for r less than r minus.
You can take
For,
that,
I mean, for in the intermediate region.
yeah, so the reason, the short answer for the reason that the geometry is stable here should be, is in essence the same as the reason the geometry is stable out here. There's a mechanism for perturbations out here to be to disappear. They can be radiated inside the black hole or radiated to infinity. Same thing happens right here. If I have any perturbation right here at some finite value of r, which is not necessarily very close to r minus, that perturbation it propagates either to r minus or inside the black hole to r equals 0 along infalling geodesics. That's all I'm claiming. Okay. So, what is known at about the geometry at r less than r minus? What is known is that the curvature in this ball, in this ball right here, grows exponentially with time. And essentially what happens is that because the radiation in here appears blue shifted to infalling observers, and there's some small flux of infalling radiation, the curvature should scale like 1 over the product of the wavelengths of the radiation squared, and that's how you get that factor of e to the twice kappa v. And ultimately what this means is that on a Penrose diagram, the Cauchy horizon is singular. And that is something that was reasoned by Penrose many years ago in the 60s, and it has been explored by a large number of authors, and I only put down a few of the more significant ones.
Excuse me, is there any chance that for some parameters the region between r minus and r plus perturbation goes cross r plus, or
Goes
to approach r plus instead of r minus? Can you go back to the previous? Seems like RG flow goes just to r minus, and r plus is just repulsive anyway.
You're asking if there's any way that I could have the geodesics approach
Yeah,
r plus.
and maybe afterward get reflected, or I don't know.
I suspect the answer is no.
Why?
Because it doesn't agree with numerical simulations. I think that's the short way of looking at it. So if you assume that the geometry out here relaxes equilibrium, and that
It seems like your R plus is really repulsive, but R minus is, attractive. So why is, do you have any physical, but both of them are horizon, right? I mean, I might be wrong, but.
I don't have a great answer for you off the top of my head. Other than to say this is what happens in numerical simulations. Right. So what is known is that the Cauchy horizon is singular. What is not known, however, is what happens in this region of the Penrose diagram right here. There is numerical evidence, however, that there is a space-like singularity formed there. Numerical evidence from many years ago. So, what is the structure of singularities in collapse? One possibility is that I have some collapsing body here. It forms an event horizon, and that the only singularity that forms in the space-time is along the Cauchy horizon. That is sufficient to satisfy the singularity theorems. Another possibility is that you end up with a singular Cauchy horizon, but with a space-like singularity at r equals 0. So my game plan for the rest of the talk, I'm going to focus on a very simple model, which is spherically symmetric charge scalar field, and I'm going to assume I'm going to make two simple assumptions. One, that there's infalling scalar radiation that decays with some power of advanced time v, and the second assumption is the one that everybody's been griping about, is that the geometry at r greater than r minus relaxes to the Reisner-Nordstrom solution at late times. So both of these assumptions are supported by numerical simulations. I'll just say that at the moment. And I claim that with these two assumptions right here, it is inevitable that the singular structure of the space-time is as displayed here, that there is a space-like singularity. That's what I want to convince you of throughout the rest of this talk. Any more questions? So let me come back to this firewall, if you will, that exists at r minus. So I'm assuming that the geometry exterior to R minus is at sufficiently late times, just given by the Reisner-Nordstrom solution. By the way, within this one particular model of a scalar field, this is just natural. There's just no way for you would need to introduce some exotic matter in order to not have geodesics behave exactly like this in this particular model. So outgoing, if there's any outgoing radiation which is excited here, it must become arbitrarily blue shifted near R equals R minus in an exponentially thin and exponentially blue shifted layer. And if you think about what this means from the perspective of infalling observers, if I'm an infalling observer jumping into the black hole, I'll encounter a very, very energetic shell of radiation at R minus, and via Raycher-Hurdy's equation, that shell focuses infalling geodesics to R equals 0. And if you work through the details, time-like geodesics are focused to R equals 0 over a proper time, which is exponentially small, e to the minus kappa v. What this means is that once you encounter this surface right here, you get ripped apart by gravitational tidal forces, and your ashes get dispersed to R equals 0 in an exponentially short proper time, something that becomes Planckian. Null curves do more or less the same thing, except for it's not proper time, but it's an affine parameter. The affine distance from this surface to R equals 0 decreases exponentially. Now, all of this is true irrespective of what the geometry is behind this blue shaded region. And it's true because Raycher-Hurdy's equation tells you, in essence, that these scalings relations have to be satisfied at the very least. If I add any matter here, it only increases these scaling relations and makes them faster, as long as the matter satisfies certain energy conditions. So at the end of the day, whenever you see something becoming exponentially small like that, it suggests that there exists some sort of expansion parameter in the problem. And in particular, it suggests that there should exist some nice late time expansion. Okay? Are there any questions? All right, so my setup for what follows is to choose infalling Eddington-Finkelstein coordinates, where again lines of constant v are infalling null geodesics. My radial coordinate is lambda, and r is again an areal function. In this coordinate system, outgoing null geodesics satisfy this differential equation. And crucially, infalling null geodesics are just given by lines of constant v. And the important point here is that they are affinely parameterized by my radial coordinate. So in particular, my radial coordinate is just the arc length, if you will, along infalling null geodesics. And I just told you in the previous slide that you should expect that arc length to become exponentially small inside R minus. And what that suggests is that in this coordinate system, I should be able to solve Einstein's equations with a derivative expansion. So in particular, you introduce some bookkeeping parameter epsilon, you assume that prime equals lambda, lambda derivatives scale like 1 over epsilon, and derivatives along outgoing geodesics are order 1, and you just solve Einstein's equations in this expansion. The expansion is self-consistent in the following sense. If I consider any outgoing null surface in the space-time, say one that asymptotes to R minus, I can solve the equations of motion near this surface M, and the dynamical degree of freedom here, which is just the scalar, reduces to an outgoing component and an infalling component, and the derivative of the outgoing component is proportional to e to the kappa v, which supports identifying my expansion parameter with e to the kappa v. Okay? So in other words, at late enough times, it's inevitable that there is some expansion parameter epsilon, e to the kappa v, which renders this approximation very good. Arbitrarily good as you approach the Cauchy horizon. So, with that said, let me explore the causal structure of the space-time inside R minus. I'm going to try and limit this to as few components of Einstein's equations as possible in order to make it followable. This one component of Einstein's equations is an ordinary differential equation in lambda for the directional derivative of r along outgoing null geodesics. This piece right here is just the electric field. So within this derivative expansion, the lambda derivatives are arbitrarily large compared to the electric field. So neglect that term. We'll come back to whether or not that was reasonable in a moment. You can then immediately integrate this equation for the directional derivative and get that the directional derivative is some constant of integration that depends on time divided by r. Now there's one other component of Einstein's equations that I'll write down, which is a constraint equation. It is a second order equation for r. It's a directional derivative along outgoing geodesics squared, and it's sourced by the scalar field. If I evaluate that equation on an outgoing null surface, say one that approaches r minus right here, this outgoing null surface, then this directional derivative, I can replace one of these directional derivatives just with an ordinary derivative, and I can replace A prime with the surface gravity on this surface right here. And if I substitute this into here, this just becomes an ordinary differential equation for zeta on this surface. And with my assumption of power law infalling scalar radiation, you can just integrate this to get zeta scaling like plus v to the minus 2p. Now, with all that work done, which I'm sure everybody followed all the details, we can explore the trajectory of outgoing null geodesics. The outgoing null geodesic equation is just d plus r, is the total time derivative, scaling like this right here. And you can immediately integrate that and get that r squared scales like a constant plus this particular power of v. So at the end of the day, what this tells you is that null geodesics, outgoing null geodesics inside r minus, essentially stay at constant radius. They don't fall into r equals 0 generally, and they don't go out to larger values of r either. So to put this in a Penrose diagram, there is a Cauchy horizon right here, where there's a distribution of outgoing null light rays that end on it, with r minus right here and r equals 0 there. And in particular, if you look at this solution right here, long enough, you'll see there is a critical solution where this constant is 0. And for that critical solution, the corresponding outgoing null geodesic ends at r equals 0 at infinite time. Okay.
So your kappa doesn't depend on v, or?
It goes to a constant at late times, right? It will have some weak v dependence, right? So, oops, sorry. So all geodesics that are inside this critical radius, RC, end at r equals 0 in a finite time. And that suggests that r equals 0 is in fact a space-like singularity. Now, you should be questioning whether or not, though, it was reasonable to cross this term out here and neglect it, because the electric field can diverge like 1 over r squared, so that term can diverge collectively as 1 over r squared. And so I had something that I argued to you was exponentially large compared to something that actually diverges at r equals 0. So is it actually reasonable to ignore that term? And the answer turns out to be yes. And the reason it turns out to be yes, I'll say it physically and then I'll show you in the equations. What ends up happening, well, I told you already that there's a shell of energy right here, r minus, that focuses light rays from here to here at least as fast as e to the minus kappa v. It turns out that infalling scalar radiation within this radius RC further enhances the focusing of geodesics and does so in such a manner that derivatives with respect to lambda are at late enough times arbitrarily large compared to any 1 over r divergence with finite power. So you can change variables from lambda to r, and when you do that, something absolutely remarkable happens, and that is that the scalar equation of motion completely decouples from all of the degrees of freedom. It becomes a completely decoupled linear PDE. That's not to say that there's no back reaction of the scalar field on itself. The scalar field is back reacting on itself insofar as there's this zeta dependence here, which arises purely from scalar radiation falling into the black hole. You can integrate this PDE, and numerically it's straightforward to do. Let me just reason analytically, sloppily, admittedly, what the following behavior is. Outside of this critical radius RC, you can neglect radial derivatives because zeta is small, and you can integrate this equation, and up to a constant of integration, the behavior of our scalar field is as follows. It decays like 1 minus v to the 1 minus p. This power p here is just coming from a boundary condition that there's infalling scalar radiation, and it grows like 1 over r. Inside of RC, you can ignore time derivatives here because it's 1 over r divergence from here, and you can just integrate this equation and get that psi scales like the logarithm of r with some function of time multiplying. You can match these two solutions onto each other at r equals rc, and the p dependence of rc exactly cancels out that p dependence there. And at the end of the day, this tells you that at this surface right here, the scalar field is going to grow in time like square root v. So in other words, infalling null radiation that's coming into the black hole results in a cloud of scalar radiation forming near RC, which is growing in time, unboundedly large in time. And at the end of the day, this means that our scalar field inside this critical radius grows like square root v times log r. Okay? Now you can plug that into Ray-Chahuri's equation now, and at the end of the day, what Ray-Chahuri's equation tells you is that if I'm looking at some null geodesic coming in, the radial derivatives along that null geodesic grow like this. They grow like r to the minus alpha v, where alpha is just some constant that depends on the strength of radiation coming in, times the exponential we started with before. Okay? Now this enhancement right here is the key point here. That enhancement means that this derivative expansion that I've written down will work all the way to r equals 0, so long as alpha times v is greater than 2. Okay? And ultimately that just means I have to wait long enough. I have to wait long enough. This expansion I've written down is a late time expansion. What this means is that at late enough times, the expansion works all the way to r equals 0.
Sorry, where did alpha v greater than 2? I'm sorry, I'm missing that. Why is alpha v greater than 2?
So let me go back to the previous slide. So I've neglected this term up here, which is written down here, r squared e squared. This term right here diverges like 1 over r squared. There's a radial derivative here. So I need this term right here, this radial derivative, to diverge faster than 1 over r squared. Right. So ultimately what this means is that at late enough times, it is inevitable that there will be a space-like singularity at r equals 0. There's just no way around it. Okay? So what does the curvature look like? The simplest curvature invariant to look at is the Ricci scalar. The Ricci scalar is just the radial derivative of the scalar field times the directional derivative along outgoing geodesics. And generically, inside of this surface r minus, the Ricci scalar blows up exponentially like e to the kappa v times this power law decaying radiation. This just comes from large radial derivatives here, large lambda derivatives. Inside of the critical radius RC, there's an enhancement by this factor of r to the minus alpha v.
Is there still a focusing inside? You said there's a focusing when you cross, the infalling matter crosses the inner horizon, right?
Yes.
Does that continue after you cross the RC?
It gets enhanced at RC to this factor right here.
I see.
Right. So the strength of the singularity is in fact growing with time. It's becoming very, very strong. It's dramatically different than what it looks like in Schwarzschild, of course. In Schwarzschild, this is just, if I look at the Kretschmann scalar, this is just 1/r to the 6th or something like that. And by the way, if you look at the Kretschmann scalar instead of the Ricci scalar here, all these scalings apply. You just square everything that I've written down. Andy?
Wait, so the red line, the diagonal red line there on the Penrose diagram, that's R plus? That's
This is not R plus. In fact, R plus is just a point right here.
so what is R there?
So R is running from R plus, sorry, R minus.
Sorry. Right.
R plus is going to, the event horizon will asymptote
Right.
to R plus, and then R minus runs from, R minus is also at this point, and the Cauchy horizon, sorry, I misunderstood your question. The Cauchy horizon runs from R minus to R equals 0. Right.
And stuff coming up from there won't interfere with the analysis? at
Stuff
R equals
coming
0?
up from where? From here?
From just below that diagonal red line.
So stuff coming up from this way?
Yeah,
Well, this stuff was crucial to the analysis, right?
yeah, that's what you're
Right.
using.
So
yeah.
so the infalling radiation was crucial to the analysis.
Right.
If we back up here, sorry, this is the problem with having multi-step slides. There's a retardation effect. So the infalling null radiation gave us this scaling right here. This power P was in there, and it was also in the critical radius RC. And it is in fact what is responsible for everything that appears on this slide right here, this extra focusing that occurs inside this critical radius. So you can't get this without it. So in particular, if you this analysis was valid in asymptotically flat space. If you look at solutions, if you look at the same problem in de Sitter space, Price's law changes from power law to exponential. And it's not clear that this type of analysis will actually work because you don't have strong infalling radiation. So I've said everything here for Reisner-Nordstrom. How much of this generalizes to Kerr? It turns out that as long as I'm considering Einstein's equations plus a massless scalar, all of it generalizes to Kerr almost identically. So why does that work? Well, first of all, the scalar influx of radiation decays slower than gravitational waves. So that tells you you can ignore gravitational waves by and large. You can solve the equations of motion with the derivative expansion in lambda, just as I did earlier. And whereas in Kerr, the equations of motion are 3 plus 1 dimensional, within the derivative expansion, they have to reduce to 1 plus 1 dimensional PDEs at each set of angles. And the reason is quite simple. If I consider, for example, time-like observers coming in, passing through R minus, they get exponentially boosted by passing through this surface because of the shock that exists there, this firewall. And they travel from here to here in an exponentially short time. And what that means is that different observers are causally disconnected from each other unless they come in at exponentially similar angles. And the same thing holds true for null curves too. And so at the end of the day, within Kerr, the scalar wave equation is the same as what I wrote down for Reisner-Nordstrom, except for there's an extra angular piece that just encodes the fact that there's frame dragging inside of a Kerr black hole. You can obviously get rid of that just by going to a rotating reference frame. And everything else that I've told you holds as well. The curvature inside R minus grows exponentially in time, and inside this critical radius, there is an enhancement of R to the minus alpha v. So there's none of that complicated structure that exists in Kerr in the textbooks, rings, singularities, closed time-like curves, and so on, exists in gravitational collapse, which you end up with is something which is, well, still complicated, but it's arguably much simpler physically. And so with that said, guys, I'm done. I will mention one quick note here that unfortunately this analysis does not generalize to vacuum equations. What ends up happening in vacuum is that you end up getting an analogous equation of motion for gravitational waves. H here is an angular component of the metric, this is a two-dimensional metric with constant determinant, what's inside the brackets here is the same linear equation that I wrote down for the scalar. What is outside the brackets is a projector onto traceless modes. If I have a function that has constant determinant, its time derivatives, its derivatives must have vanishing trace. And that makes this equation nonlinear. And ultimately what this means is that when you shine gravitational waves into the black hole, there's scattering. And that scattering results in the amplitude of gravitational waves vanishing at a discrete set of times. And that vanishing occurs at a discrete set of times, and also it is different at all sets of angles.
Is it interference?
It's scattering, so scattering interference, yeah.
It's the phase that matters?
It's whether or not this vanishes that matters. Right, okay. And so ultimately this just means that your derivative expansion breaks down when r becomes some exponentially small number, and we can't say anything about what happens at r equals 0. It seems, at the moment, that the situation is that there is a space-like singularity there, which is similar to a BKL singularity. And with that said, I'll end and say thank you.
So there is an independent issue of stability of the metric. So suppose, I mean, you assume it's spherical symmetry and so forth. And,
only for the purpose of giving this talk, did I assume
right,
spherical
but my
symmetry.
question is, suppose you deviate from the background metric that you assume. Is it stable or unstable?
So if you ask a mathematician, they'll say they don't know the answer. Right? I'm assuming you're talking about the exterior geometry, the exterior to R minus. If you ask a mathematician, they'll tell you they don't know the answer. I don't know of any physicists that strongly believe the answer is that it's unstable. And it
But you can check numerically.
You can check numerically, and it agrees with numerics. The exterior region is stable. Right? And in fact, so let me just show you this simulation from Perron and Hod from 20 years ago. This is gravitational collapse. And this simulation, this plot I'm showing you just shows the congruence of outgoing null geodesics. So prior to collapse, all the geodesics are going outwards. At collapse, some geodesics fall into R equals 0. And then long afterwards, where this analysis that I told you about is supposed to be valid, you'll see that there's a bifurcation in outgoing geodesics. Some geodesics escape to infinity, some don't. This is where you might want to call R plus. And then outgoing geodesics in this region pile up on some surface R minus, right here. It's roughly right here. And inside, as far as you can tell just from eyeballing it, outgoing null geodesics all stay at constant R, which is exactly what this analysis says that should happen. Okay. And they, of course, saw evidence here for a space-like singularity here. It's going to be very hard, actually, to see the curvature grow like R to the minus alpha V in numerics, but that's what it should be.
So, Paul, I have a question. First, the comment, what I really like about this analysis, it has always bugged me that the uncharged spherical black hole is a Schwarzschild, got a nice space-like singularity, and then you put the slightest amount of charge and go look at the textbook, you get Reisner-Nordstrom, no space-like singularity, it's got a Cauchy horizon, and maybe time-like singularities, all sorts of crazy nonsense. And that didn't make sense because there ought to be a continuity with what one feels. And in some sense, I think your picture shows, in fact, the charged guy has got both the space-like singularity and a Cauchy horizon joining up.
Mm-hmm.
And which fellow is bigger or smaller? I mean, I can imagine now a continuity that will go from a lot of Cauchy horizon to a lot of space-like singularity.
So,
but let me ask my question before you go. So my question now is the following. The Kretschmann scale, right? I know what it is for the Schwarzschild case. And I think you said that it behaves differently here. In fact, it diverges or something for this space-like singularity. That seems to violate this this continuity picture that I'm looking for.
I don't think it does, actually.
So are you saying that this Kretschmann will in fact look like the Schwarzschild Kretschmann for your space-like
So
singularity?
outside of R minus,
Yeah.
it does. And as I take the limit where my charge goes to 0, R minus goes to R
No, I
equals
want
0.
to look at R equal to 0. That's where I want the thing to look like a Schwarzschild singularity.
In that case, it's not a.
Isn't that a worry? I mean, I would have, because I want this space-like
Schwarzschild-
singularity to look
Schwarzschild-
like Schwarzschild.
You can want all sorts of different things.
It's just a matter of continuity. Right? I got a knob that I turn.
So Schwarzschild is special.
The charge itself is like.
No, but Ramesh wants it to continue.
Continuously, that's all I'm
So
asking.
the only part that is going to, as far as I can tell from this analysis and from numerics and so on, the only part that is going to continuously approach Schwarzschild is the region exterior to R minus. The rest of it will not. This is all just dramatically
We
different.
think it's a phase transition between zero charge and.
I think Schwarzschild is unstable. I think that's the way I would put it. Schwarzschild is not a stable solution. If I give it an infinitesimal amount of angular momentum, it's different. It's different. There's an R minus, and inside R minus, the solution is just different.
Okay, Paul, I think you need another paper. You got to solve this other problem.
No, but
And if the charge
It
itself
might-
is discrete, then what does it matter?
I'm sure Andy has got some thoughts.
It might, but you're making that based on looking at in the space of axisymmetric solutions, right?
No.
If you look
No,
at
no,
all
no,
perturbations
This
for Schwarzschild, right? There's a statement about Schwarzschild being, if you do a generic perturbation,
If you do a generic perturbation,
Time
you will
dependent.
add angular momentum.
right? But it won't be.
Generic.
It won't be exactly Kerr.
At
So
late-
you don't know that you're changing the nature of the singularity, do
At
you?
late times, so if I take Schwarzschild and I do a generic perturbation of it that adds angular momentum, okay? So for example, I add a scalar field and I turn on some scalar field that imparts some angular momentum.
Yeah.
This analysis holds, and everything works out identical to what I told you here. Okay, and the interior geometry to whatever R minus there is will look as I told you here. It will not look like Schwarzschild.
Wait, but this does look kind of like Schwarzschild. This looks more like Schwarzschild than what Reisner-Nordstrom did.
Well, in the sense that there's a space-like singularity, yeah. But the growth of the curvature near R equals 0 is just completely different. The strength of the singularity grows as a function of time. It's completely different, and that is due to this infalling radiation. Right? There's infalling radiation which is decaying with the power of time. You would think it's negligible, but near R equals 0 in this little region of radius RC, which is shrinking as a function of time, that radiation is non-negligible. There's just no way around it.
Well, but you're saying that's like, but I mean, just to make a more refined statement, that people would say the exterior of Schwarzschild is stable, in the sense that the exterior is self-done.
Yeah.
But the interior, I mean, long ago, there's people, chaos near singularity. That's an instability, right? People discuss chaos near singularities.
It would be
Small
like a BKL
perturbations.
singularity, right?
Yeah. So this is kind of like that.
Yeah,
isn't it?
so it is kind of like it, except for the presence of the scalar field tames the chaotic behavior of the BKL singularity. And that was pointed out by one of the authors, I think it was B, in the 70s, that the scalar field actually tames that chaotic behavior. So.
Let's close the discussion, I guess, and let's thank our speakers again.
Yeah, that's
So this is the secret.
Oh, I know.
This is the secret. Let people sit down.
Yeah,
Another half hour.
He's probably up for
Yeah, I guess so. Unless if you want to chat, I'm saying that I have to go, but
I don't know here at the BHI-Harvard0. We've done office round.
oh, okay, yeah, it was nice to meet you.
Very good.
Yeah. You can watch his talk later.
But this was not the Penrose diagram. The diagram that he showed. The diagram of the emerging of the. Well, I mean, these weren't all possible due to. I don't know how serious I am.
Is it okay if I come to
Yeah. So the ones that are exterior or not.
First of all,
Okay, I guess I wanted to talk to
not
him.
going this way. You know,
But it sounds like
everybody just plugs in their own.
all the way to R equals 0. When you get this radiation between exponential.
For the science?
No, definitely you can't cross it. Definitely. You can
Right,
be an
so there's a
outside
plot in
observer
that
that jumps to black hole and then you cross it.
I had some objections
But
too.
I think-
Yeah.
but I think-
But
And
it
another
doesn't
thing
say anything about
that
any
you
stuff. So the particular plane
of
is
point
the plot.
rays that
Some
is
others
cross
read about it.
out
It's
down
in
the
the paper,
line,
but
get reflected and then cross
And
the
everything works out
minus.
exactly
So
the
it
same.
should be much
Exactly
more
the same.
complicated.
It's just
than
kappa is going to 0.
drawing
Well, but
some
it's-
lines like that
Yeah.
anyway.
Yeah, it's a family of lines like this.
Yeah.
I
Right, in the figure you showed.
Oh, this the firewall?
Or this one?
This one.
Yeah.
Yeah, that was worked out a while ago.
Why would you
for
assume
Lisa
that
Rice and Orchard?
the last
This
image
firewall.
that you
No one
see
has ever called it a firewall.
is from Disco?
Well, yeah, there's that. And lots of reasons that the ISCO is probably not a well-motivated figure for
First of all, yeah,
Energetic
so this
currents.
black curve is not a meaningful curve.